Hi guys, I'm Liam and this is
I'm Foster.
and we will be going over the 2017 final examination for MATA37. So let's go to the first question. So these are a bunch of true-false questions. We don't have to show any work, so we'll just discuss what we think the answers are. So here it says, suppose that g prime and h prime are continuous functions, then this integral is equal to this. Um, Interesting. So one thing that we know is that the integral will give us a function whose derivative is equal to the original function, right? So my first thought is we can try and differentiate this one and see if we get the function on the inside, right? So I think that this is actually going to be wrong because they're forgetting that in chain rule you also have to multiply by h prime x, right? So we can try and differentiate g of h of x, right?
Yep.
And when we do that by chain rule, we know it's going to be g prime hx, which is what they have, which is good. But then we also have to multiply by h prime x, which because that's not here, we know that this is going to be false. This is obviously wait. Every continuous function is integrable.
This is right. I don't know. It's differentiable.
No, differentiability implies continuity. Continuity does not necessarily imply it. I'm pretty sure.
Okay.
Of course not. Like for example, in this case, right? It's continuous, but it's not differentiable at this point, right?
I see.
Yeah. Good. But this question is asking about integrability. Is there a continuous function that is not integrable? That seems true. That every continuous function is integrable.
Sine function work with exponential.
I mean, it must be true, right? Like you're just calculating the area under the continuous curve, right? Seems like I can't think of a situation where
Yeah.
it wouldn't be integrable. So I'm pretty sure this is true. Next question. Okay. If f prime is a continuous decreasing function on 2 to infinity, and the limit as x tends to infinity is 0, it's continuous decreasing and it's approaching 0, then the integral is convergent. So this is obviously false, right? We can think of the example of 1 over x, right? If we integrate 1 over x from 2 to infinity, right? They're saying f prime is a continuous decreasing function, which in this case it is. It's going to be minus 1 over x squared. And of course this is always positive, so the whole thing is always negative, right? On 2 to infinity, right? X is never 0. So this is a continuous decreasing function. F prime. Oh, they're talking about f prime, not f.
This is f prime. 1 over.
Yeah.
It's good. And it's decreasing. Right?
1 over x squared. No, this is increasing, I think.
Oh, increase.
Yeah.
From
It looks
negative
like this, right?
to approach to negative.
So that's not good. So they're giving us information on the.
Can we just add a minus sign here? The negative of 1 over f.
I see. So in this case, if we have this one,
Then f
prime is just positive 1 over x squared.
And it's decreasing.
This is a f prime x is it is continuous on 2 to infinity. It is decreasing on 2 to infinity. We can prove by taking the next derivative, right, if we really wanted to, and that would be minus 2 over x cubed, right? Just by power rule, x to the minus 2, and we bring this here and make this minus 3, right? And we see that this function is always going to be negative when x is greater or equal to 2, because this is always going to be positive when x is greater or equal to 2. So the whole thing will be negative. So we know it's decreasing always. It is continuous, obviously, because the limit as of 1 over a squared the limit of 1 over x squared as x approaches a will be 1 over a squared for all x in this interval. This is easy to prove if you want to. and we have that the limit is 0, right? So all of this is true for minus 1 over x. However, we know that minus 1 over x corresponds to the harmonic p series, and we know that the p series test proves that convergence is that they're dependent on each other. There's a dependency. The integral is the convergence if and only if its corresponding series is convergent as well, and we know that the series of 1 over x will, this is just the harmonic series, which will diverge. So therefore this is false. Okay, next question. We have the integral from 0 to 3 of 1 over x minus 1, and it's asked, oh, they're just actually doing it, okay. Well, this looks true, right? And this is correct. I think it's right. Everything looks right. You do the ln, because the derivative of ln of x of the absolute
From
exponent.
0 to 1, this term is negative. From 1 to from 1 to 3, this term is positive. Does that matter to this question?
They're just asking us if their steps are correct, right? So for me, like the function 1 over x minus 1, right? It's
Because there's a discontinuity at the x equals 1.
oh, you're right. This is an improper integral, right?
Yeah.
So we should yeah, we need the discontinuity to be in our interval, so we should split it into 0 to 1 of 1 over x minus 1 plus the integral from 1. This is a very good point. This could trick people. I think he's right. It's probably going to be false. It's probably a trick question. So this is a very good thing to keep in mind. Yeah. Whenever you watch out for type 1 and type 2 improper integrals. This is a type 2 improper integral, which means that you have a discontinuity at a point, and a type 1 improper integral means that one of the sides is infinity or minus infinity. So we have like this, dx. Okay, so here we should take the limit as a approaches 1 from the right, from the left, sorry. 1 approaches from the left of ln of x minus 1. They did do this part correctly, right? Evaluated from 0 to a. And then we should add the limit as a approaches 1 this time from the right of ln of x minus 1, evaluated from a to 3, right? So we'll get, let's go, okay, I'll just keep writing in this question, then I'll erase it after I'm done. You can pause the video if you'll need it. So on this side we are, okay, we have ln of 1 minus 1 minus ln of the absolute value of 0 minus 1 plus ln of 2, as they said, minus ln of 1 plus minus 1. Okay. So in this case, we have 1 minus 1 is going to be just less than 0, so this is actually just undefined. And this term is also going, this term is defined because as you're approaching 0 from the right, that's just going to be actually negative infinity, right? If you think of the logarithm function, it looks something like this. Right. So if we're approaching 0, because this is just 0 plus, right? So if we're approaching 0 from the right, that's defined, and that is equal to negative infinity. But the problem here is that we're approaching, this is equal to 0 minus, right? Because this is slightly less than 1, so we're going to have a negative term. The problem is you can't really approach 0 from the negative side. That's not possible because it's not defined here, right? So I believe that this term is just not defined. Like here we can say it's minus. Do you have any?
Can we first pull a minus sign here out? So this would be 1 minus x. So there will not be undefined things. If we pull a minus sign here, So this term becomes 1 over 1 minus x.
I see
So
what you're saying. Yeah, that's a very good idea. We make it 1 minus x and we pull out a minus sign, right? So then that means that we're going to have minus on this whole part of the thing, right? But now we get to have 0 plus, right? So that's really
from
good
here
idea.
is 1 minus x.
Yeah. So this is going to be different. We will have 1 minus, and here we will have 1 minus. I can rewrite it as you said. Okay. So now we will have our 0 plus, which is what we want. So this is negative infinity. Yeah. And then okay. So what's good is that this term is just going to be positive infinity, right? Because you have minus infinity, right? And on this side, we're going to have the same thing. Yeah, ln of 1 is just 0, right? So we're going to have minus. So infinity plus infinity will be infinity, right? So we do know that this answer will diverge and it will not be equal to ln of 2. The problem is that you can run into, in this case we're lucky that it's positive infinity plus positive. If you have positive infinity minus negative infinity, you don't know anything because one of the infinities might be bigger or smaller than the other, so that's actually indeterminate. But we're lucky in this case that we have positive.
Maybe we can combine them together to write the t here and the t here, and then because it's minus, so
we have positive infinity plus positive infinity, right? So we're lucky. We know for sure it will diverge. So definitely can't be equal to ln 2, right? So the answer is false. Okay. Just make sure this is running. Okay. If a n and bn are both divergent, then a n bn is divergent. This seems to be false. We know that the series 1 over... oh, these are sequences, not series. Sorry, right? Oh, this is definitely false. Because we can think of something like 1 minus 1, 1 minus 1, and here we're going to have minus 1, 1, minus 1, 1, right? So these both diverge, but when you multiply, it's just minus 1, minus 1, minus 1, which converges, right? So if an equals minus 1 to the n, and bn equals minus 1 to the n plus 1, then when you multiply them together, you're going to have minus 1 to the power of 2n plus 1. And since this is an odd number, this is just minus 1. And the limit of minus 1 as n approaches infinity, since minus 1 is independent of n. Like, you could do delta epsilon proof it. This is just a true or false. So that's obviously not necessary. The answer is false. This will converge. Every convergent series has a unique sum. Yes, by definition, a convergent series is one where the sum of the partials of your sequence, right? The limit as n approaches infinity, right, will be equal to some unique sum, right? That's by definition. If for a convergent series, right? Okay. So this is just true by definition. Okay. We can compute that the integral from 1 to infinity is equal to 1. So we may infer that from the integral test that this is equal to 1. False. This is very false. The integral test tells us that this will converge to something, right? But it tells us nothing about what it will converge to. This is because if you think about it, right? Say you have something like 1 over x squared, right? Of course, if I take the whole area, that's obviously going to be more than if I take
rectangle.
This plus this plus this, right? Like, actually, I mean, this is even, we're just summing these heights. Like, we're doing something completely different. Here we're summing the height,
and height here times the 1 still be the height, so times the 1, so be the rectangle here. So there will be extra area above this curve.
Yeah, you're right. We're technically multiplying it by 1. We're multiplying the height by 1, right? So of course these rectangles are not going to be the same as
The area of curve.
as the area of the curve, right? Necessarily, they could be, right, but they're not necessarily. And we could do counterexample, but I think that it's very clear that this is a false. Okay. Suppose the end diverges. Then okay, c equals 0, false. Dumb question. This is a really stupid question. They never said c does not equal. If c is not 0, this seems true to me, because you can just like factor the c out, and then any constant times something that diverges should be right. But in the case, there's one counterexample which is c equal to. The Maclaurin series for this is equal to this. I am not 100% sure on the definition of Maclaurin series. Do you know?
Okay, so the convergence center of the Taylor series is 0.
Yes. This one can have any center.
This one means a equals 0.
Oh, Maclaurin centers at 0. Taylor
Yeah.
can center anywhere.
Yeah.
Okay. And is the definition f of x to the n over n factorial times x to the n? Is that the definition of the...
Yes, because we have to know what is the derivative of f of x.
Mhm.
Do you know what it is?
It's 2 to the x times ln 2.
Yeah. Okay. What's the, for example, the
The nth derivative. The nth derivative of f
Yes.
of x is
Okay.
ln 2 to the n.
What's the general term for the nth derivative of f of x?
Ln 2 to the n times 2 to the n. Times
Time 2 to the
To the
x.
x,
But
yeah.
we plug a equal to 0, so 2 to the 0 is 1. So there is
I
no
see. So this is centered at 1, you're saying?
center at 0, a equals 0.
I see, yeah. And then to the power of 0 as well.
If it's Taylor series, then in general, this will not be x to the power n, it will be x minus a to the power n. But a is 0, so x to the power n.
So this is actually a Taylor series, right?
Yep.
But all Taylor series are Maclaurin series. Taylor series is a subset of Maclaurin series.
No, inverse.
Inverse? Oh, Maclaurin always at 0.
Yeah.
Okay. Yeah.
Taylor series for a equals to any real number.
I see. So Maclaurin is a subset of Taylor's.
Yeah.
Cool. Next question. The sum from n equals 1 to infinity of this thing equals this.
First, what's the ratio for
Yeah.
n?
If we put in 1, we'll see that
R is less than 1.
Yeah, a we don't actually have to calculate a, but whatever, let's do it. So a is equal to 2 pi over 5, right? That's our a value. We have an a value, and since we have an r value, which is equal to pi over 5, right? So since we found both of these things, we can find r by doing the 2 to the power over 5 to the n minus 1,
Okay.
and we to the n plus 1. This cancels, this cancels. So we see that our ratio is pi over 5,
So
right?
according to that stupid formula, which is a over
1 minus n. So
which is
we see that in this case that is 2. Oh, we actually needed our a value, right? Yeah. 1. We weren't just usually if you're just checking if it converges or diverges, you just care about the error. But if you want to find exactly what it is, then you use this, right?
so this is true.
Okay. Well, let's see if it's actually equal to it. I'm sure you already did it in your head. let me catch up to you. 2 pi
Oh
over
no,
5
this is false.
times 5 minus pi over 5.
This is false.
Okay.
The numerator is 2 pi.
So we have 2 pi over 5 minus pi. And false. Yes. Okay. Will that function f from R to R be defined as such? This is a what do you remember the name of this function? So it starts with a d. However, this is a d.
Something wise, piecewise.
No, yeah, it's piecewise function, but the specific thing where we split into irrational and irrational, called after some guy that starts with d, whatever. Use integrability reformulation to prove that f is not integrable on 0 to 2. Make sure to fully justify rule. So the integrability reformulation states that I'm going to state the contrapositive of the integrability reformulation. You could state the version of it where you're saying if it is integrable, but because it's if and only if statement, we can just take the converse of both sides to get the. Or you could call it contrapositive or converse for a double implication. They mean the same thing. Converse and contrapositive. So anyway, we show that for all epsilon greater than 0, or sorry, there exists, because we're doing the converse, right? There exists epsilon greater than 0, such that for all partitions of our interval, which is 0 to 2. All partitions, I'll state here that P is a Riemann partition of 0 to 2. Okay, such that for all P, the upper Darboux sum of Fp minus the lower Darboux sum of Fp will be greater or equal to epsilon. Right? This is the reformulation. This is what we have to prove to show that our function is not integral. So, So how can we do this? So we should start by taking an arbitrary Riemann partition. Take arbitrary P. I'll write the final P, so I'll just say take arbitrary P. Take arbitrary P. We want to find the upper Darboux sum and the lower Darboux sum. So the upper Darboux sum is going to be equal to the sum of mi times xi minus xi minus 1. From n equals 1 to I equals 1 to n. And I will explain a little bit more about what this means. So we're taking an arbitrary partition equals xi, where I ranges from 0 to n, right? So we have our arbitrary P here. So basically what we're doing is we're looping through the indices, the i's, right? Other than 0, we're excluding 0. And we want to choose an mi. What is mi? Mi is defined as the supremum of all of the values that f of x attains during its interval from I minus 1 to I. So basically, we're looking at the interval. The first one we start with 1. M of 1 is equal to, look at the interval of f of x from 0 to 1, and we want to find the supremum, because this is the upper Darboux sum, right? This way, we're definitely going to get either an overestimation or an exact amount of the area, right? So it's, yeah. Like for example, in an increasing function, when you take the right Riemann sum, you're going to have an over thing, and for the left it's going to be underestimation, but that's if it's always increasing, right? So in this case, no matter what the function is doing, because we're always taking the highest value, this one will always be an overestimation, right? So mi is defined as the supremum of f of x such that x is an element of xi minus 1 to x. Right, this is what mi is defined as, right? Now, this is where we use the density of R to conclude that this set will be equal to both of these values, right? I'm just going to say, like, 3 plus E is approximately equal to 5.71, right? Just to make, like, you don't have to do this. You probably shouldn't, I guess it's not rigorous, but just to show that this is clearly not equal to 1, right? It's probably useless, but we can say by the density of R, by density of Q, of rational numbers and irrational numbers in R, right? We know that in any interval, we know but like xi minus 1 has to be less than xi, right? Like we know delta x is greater than 0. That's the thing. Delta x might be approaching 0, but it is greater than 0, right? It has to be greater. The moment that you take delta x to be 0, you have nothing, right? So that's why we always deal with limits. So we know that this has some limits. There are infinite real numbers in this interval, and in any interval with infinite real numbers that are like next to each other, we will definitely have both irrational and rational. We know by density of Q and I and R, we know in any interval xi minus 1 to xi, x will be an element of Q, and there will exist x that's an element of Q, and there will exist x that's an element of for any x in this, there will exist this and there will exist this, right? So therefore we know that this function will hit both of these values, right? During that interval. Fx can only be equal to a maximum of two things, and it will achieve both of those things, right? So now we have mi equals the supremum of 5.7. I'll just write 3 plus e, whatever. 3 plus e and 1. Now I will say that that therefore mi should be equal to 3 plus e. And I will say because the supremum of a finite number of elements is just going to be equal to the maximum of that set, and in that case that's 3 plus e. So for the exact same reason, we have mi is the small mi, right? We have the lower Durbo sum is equal to the same thing, but with mi, right? In this case, we want to take the infimum of the same set, and that is just going to be equal to 1, right? It's equal to the infimum of the set of 1 and 3 plus e, and that's going to be equal to 1. So we have our, so this is for any mi and any lowercase mi, they're equal to one specific number, right? So that's really, really good for us, because that means that we can easily use the constant multiple rule of sigma, of summations, right? When you have a sum and there's a constant factor in all of those in all of the things that you're summing, you can factor that out. It's called the constant multiple rule, right? We know that mi is equal to 3 plus e. We can factor that 3 plus e out, and we have the sum of xi minus xi minus 1, and L is equal to 1. We can factor out the 1. Okay, that's kind of redundant, but whatever. Times the same thing, right? And we see now that this is just geometrically, we're just summing the lengths of the partitions for all of the partitions. Because we start with 1, so it's going to be x1 minus x0. That's going to be the length of the first partition. And then we're going to have the length of the second partition. And we're going to go over the whole thing. And we said that P is a Riemann partition from 0 to 2. Therefore, we know that this whole thing is just going to be 2. And it's going to be the same thing in the other one. So we actually know that the upper is going to be equal to 3 plus e times 2. For an arbitrary partition, this is true, is equal to 1 times 2, which is 2. And then we know that we want to prove this thing. We see that the upper minus the lower is equal to... This is greater than 0, obviously. You can see that by factoring out 2 if you want, and then getting 3 plus e minus 1. Yeah. And then that's just 2 times 2 plus e, right? Yeah. That's just, we can write that as 4 plus 2e, right? So then we can just choose our epsilon to be this thing, and since we will have our epsilon be equal to our u minus lp, we have proven that f is not integrable on 0 to 2. Okay, next question. Consider the sequence defined like this. If n is greater or equal to 1 and a1 equals 1, suppose that an does it converge or diverge. An is less than 6 for all n, does an converge or diverge? Okay, so in this case I want to use bounded monotone convergence theorem to show that this will converge, right? So how can I do this? I have to show that the sequence an is always increasing. If it's always increasing, and if it's always bounded, then we know that any function that's monotone and bounded will converge, right? Or in other words, a more powerful version of the statement is that any monotonic sequence will converge if and only if it is bounded, right? Another way to think about that is if you have something that's always increasing or always decreasing and it's unbounded, that means that you're approaching infinity or negative infinity, right? But if it is bounded, then it's just going to be approaching that limit, and you can never go back down. So, like, the boundedness on the other side is implied by the fact that you're only going up. So, we're going to use BMCT, bounded monotone convergence theorem. So basically, I want to show.
Induction.
Yeah, we're gonna use induction to show this. So I want to show that
For n equals 1, the case is true, and the case is 1.
yeah, I'll show, for example, that 1 is less than is an, which is less than an plus 1, which is less than 6, right? if I can prove that this is always true, then I showed the fact that the next term will always be bigger than the last term means it's always increasing. And obviously I'm showing that in general all of the terms are going to be bounded by 1 and 6, right? So if I can show this, then I can conclude that by BMCT we have convergence. So the first is the base case, right? I want to find a of 1 and a of 2 to show that this is true in the base case. A of 1 we're given is equal to 1. And a of 2 is equal to the square root of 2 plus a of 1, which is 1, which is square root of 3. Yes.
Okay. Greater than.
So in this case, we have 1 is less than 1, which is less than root 3, which is going to be less than root 4, which is equal to 2, which is less than 6. So our base case works. Square root is a strictly increasing function, so that's why you can make this assumption. Okay. So now we should do the inductive step. So this is our inductive hypothesis, right? And we want to prove it. So
for the case
arbitrary
n plus 1.
Exactly. We want to assume our hypothesis that 1 is less than an is less than an plus 1, which is less than 6. We want to show that 1 is less than an plus 1, less than an plus 2, less than 6. If we can show that, if we assume our base case, our next thing is true, then we've shown that for all natural numbers, this is going to be true, right? And we have proven convergence. So, okay. So what I would like to do is, in this case, we know how to go from a big number to a smaller number, right? But in this case, we want to go. Oh, that's perfect, actually. We want to show. Oh yeah, because if we want to work. There's two ways you can do this. If you want, you can start at this and you can make a double implication. Yeah, that's the simpler way to do it. So let's start with what we want to show, right? And basically we want to do like this, right? We want to go in reverse from what we want to prove. If you wanted to do it forward, then you would have to basically rearrange this formula for an, which is fine. You can do that. But I'm gonna do it, I think, the simpler way, which is to start with what we want to show, and just write equivalent statements, which will imply, right? We just need this direction, but it will be equivalent statement. By definition, we know n plus 1 equals square root of 2 plus an. And by definition, that's going to be 2 plus an plus 1. Right? We can take the square of everything. Right? Like, if you think about why is this a bidirectional thing, right? Well, if I have this first statement, because everything is positive, I can take the square root. Because the square root function is strictly increasing, that means that if I plug in values that are in ascending order, my result from the square root function will also be in ascending order, right? And now, how can I go from this step to this step? Well, the x squared function is increasing on the domain of 0 to infinity. And because all these things are positive for the same region, right, that's why this is a bidirectional step. Okay? So now we can simply subtract 2 from everything. Okay, and now all we need is this, right? Because this is the point. This is the part of the thing where you can't use the bidirectional one anymore, right? Because of course, I want to put in what our assumption is, right? Which is 1 less than an less than an plus 1 less than 6, right? So I want to show that this implies what we want to show, right? So that's why the bidirectionals are important. In this case, it's very important that we just show that this implies the upper statement. Because of course you can't, like in this case, maybe an is like 0 and an plus 1 is like 30, right? So you can't go from this top statement to this bottom. But if you have the bottom statement, you can definitely go to the top. Because if an is between 1 and 6 and it's less than an plus 1, then this statement is definitely true, right? This bottom statement implies the top statement. So because we can go... Okay, just to explain it more, we have this relationship that's true, right? And then if an is greater than 1, it's definitely greater than minus 1, right? And if an plus 1 is less than 6, it's definitely less than 30, right? Okay, that's more of an explanation. So therefore, since we showed that our assumption, our inductive hypothesis, implies what we wanted to show, our proof is basically finished. We know that our hypothesis is correct. We know that 1 less than a1 less than a2 less than 6 implies that 1 is less than a2 is less than a3 is less than 6, which ... implies that 1 is less than an, for which is less than an plus 1, which is less than 6 for n is plus, right? For all n is equals. By induction. So that's perfect. So that means we are bounded by 1 and 6. In this case, yeah, because we know it's increasing, we just need to have the lower bound is implied by the fact that it's always increasing, so we just have to talk about an upper bound, and our upper bound in this case is 6. So we can say that an is less than 6 for all n, and so this is increasing, so it's bounded from above. And we didn't prove we actually proved strictly increasing in this case, but that actually has no relevance because we just need to show like we just had to show with the equal. But yeah, I mean strictly increasing, sure, like basically increasing is enough. You don't have to show strictly increasing because strictly increasing implies increasing, so but we showed strictly increasing, so I'll just mention. And since an is plus 1 is greater than an for all n, then we know that we have strictly increasing. Therefore, by bounded monotone convergence theorem, an converges. Perfect. Okay, next question. So let the sequence an be contained in R. Provide a complete and accurate definition of what it means for the series of an to conditionally converge and absolutely converge. So conditional convergence means that it doesn't absolutely converge, but it does converge, right? So I think a complete definition I think it would be better to do absolute convergence first, and we can use this definition for the top definition. So absolute convergence, this is a very easy question. We know absolute convergence means that the limit as n approaches infinity of the sum of absolute values of a. Sure. Should I pause the video? And then, yeah, I can pause. Okay, we're back. Yes, okay. So here, for something to absolutely converge, that means that the limit as n approaches infinity of the sum from the first term, whenever that may be, to the infinite term, is equal to some constant value, where C E, right? That's what it means for a sequence to for a sequence that's contained in R to absolutely converge. We could write this in terms of delta epsilon, that basically the limit of the partial sums. So for all epsilon, yeah, because they want absolute, like just give the delta epsilon just in case the TAs are picky or whatever. For all epsilon greater than 0, there exists n greater than 0, such that ne whatever, let's say nen n greater than n implies that the difference between s of n and s of n, this we can define this as s of n, right? The difference between s of n and c is less than epsilon, where and basically there needs to exist a c, right? If there exists a c where where this is true, where the above is true, then we have absolute convergence. Sorry, we need the Sn. Okay, let's define this absolute Sn. Whatever, doesn't matter. This isn't necessarily the actual notation. I'm defining it myself for this, right? If this is true, then absolute convergence. And else, if it's not true, if there does not exist C, if there does not exist C, or you can take the negation of the statement. If there exists epsilon, where for all n, blah blah blah. If the negation is true, then we don't have absolute convergence. Right? Right, and then we can just say for conditional convergence, let's define Sn to be equal to the sum of an's to infinity, right? And then we can make the exact same statement as here. I'm not going to rewrite it, but basically you'd rewrite this, but here you'd put Sn instead of this, right? If that is true, but the one with the positive Sn's is false, then we have conditional convergence. Yeah, we have conditional convergence. Else we have we don't have, right? Conditional convergence. Okay. Determine whether that series. Determine whether the series absolutely converges, conditionally converges, or diverges. Make sure to fully justify your solution. Okay. So let's think about this for a little bit. Our first thought is, would it absolutely converge? And in this case, n's are getting bigger and bigger, right? We're not gonna reach the point where it's undefined, since n starts at 10. We can never have a negative 1n. And as n gets really, really big, this is going to just approach -2. And we're gonna have -2 to the power of 5n, so that should obviously diverge, yeah. We can even do this by div test, since the general term does not approach 0. Yeah, this is a very easy question. You just do the limit of the general term, or of the sequence, right? However you want to think of it. General term is fine. As n approaches infinity, is equal to, I mean, I don't know how much justification you have to do. It's basically going to be -2 to the power of 5 times infinity, right? Which is equal to minus. Well,
we use the
this oscillates between positive and minus infinity. This is the worst kind of divergence, right? It diverges by
You can
oscillation.
rewrite this as the e to the power ln to this.
Sure.
Small form. E to the power ln.
We can write 5n here, right?
Yeah. 5n can be in the denominator to be 1 over 5. It's the next step.
Okay.
So this equals limit. Next step, we can move 5n to the denominator to be 1 over 5n.
How can we move it to the denominator? We can put it in the. No.
Eventually, we will use the L'Hopital's rule. Okay. So now if n approaches to 0,
N approaches infinity, right?
It approaches to infinity, the number inside the ln is -2.
Yeah.
Well,
We can write it as.
how can it be negative?
Yeah, we can just, because e is a continuous function, right? Because e to the x is continuous, we can just put an e to the limit as n approaches infinity over the top. 5n ln minus 2.
I see.
And over
We
n
should
plus 1,
pull the minus sign out.
which is equal to e to the power. Obviously 5n will approach infinity, right? And this will obviously approach -2, right?
But it's not defined because this number cannot be negative inside the ln.
Ooh.
So we should pull the minus sign out first to be -1 to the power 5n out of this two.
This whole thing is kind of weird then, right?
So at the beginning we should pull the -1 out of this term
Mm,
to be -1 to the power 5n outside of this.
sure. This feels like too much work. It's so obvious, right?
Otherwise, it won't be worth 4 marks.
Let me think if there's another way. Yeah, let's just do ratio test. That's easier. This is fine. If you want to just say like intuitively, it's -2 to the power of infinity, which is oscillating between plus minus infinity. That could be fine, but like you said, it's 4 marks. Maybe that's not rigorous enough. So let's just do the ratio test.
In A36, you can use root test.
Okay. Since we didn't learn about root tests, we cannot use it, even though it is pretty powerful. Okay. So we have this one. We need to show that the limit as n approaches infinity of this ratio is greater than 1.
This is not easier than the last one.
Yeah.
You could just simply pull the -1 out.
Okay. We can make this be squared and delete this, right? Oh, never mind. Don't do that. These are inside these, right? Yeah. I don't know. Oh, could we do comparison test? Comparison? No.
I don't know, because there's a power to the 5n.
Mm.
Our last resort is to pull the -1 out.
Mm. Yeah, because because we're taking absolute value, we can remove both of these by absolute value properties, right? And then we can make this be 5n times this to the 5. Yeah, I think we're basically done actually. Because we can even say that
To the power 5.
yeah. We can say that the limit, like if you think about if we think about this ratio by itself, right? We can say that the
Yeah, okay.
yeah,
Sure.
we can
Is
flip
m
it.
plus
Like,
1 and m plus 1 cancel.
we have a limit that approaches infinity of. We can basically take the 5 over n out of both of them, and then we can flip it so we have 2 times n plus 1 squared over 2n times n plus 2 times this thing. Right. Okay. Mm. I don't know. Yeah, this approach is 1, right? You can't use
What?
this approach is 1.
Wait, we can cancel out the m plus 1 here. This is m plus 1 to the power 5n. Oh no.
Yeah.
No.
It's square,
No,
right?
no, no.
You put them together, right? It's a square. Yeah.
I don't know.
Look, this one will approach 1, and this one will approach. Oh, yeah. Wait. This one approaches 2, right? Wait. Hold on. Sorry. This thing approaches 1. Approaches 1, yeah. But this one approaches 2. So a ratio is 2, right?
What? approaches to?
Yeah.
32 gets to the power 5.
Oh, sure, whatever, right. Yeah, we can write. Okay, so we have to show that this one will be 1 and this one will be, like you said, 32 times yeah, n plus 1 over n plus 2 to the 5.
And formally, we should divide the n to the power 5 in a from the numerator and denominator. We want to write
You
it
should
on
do what?
divide n to the power 5 from the numerator and
Ah, that's a
denominator.
smart idea. Yes. Um, okay, so we also have to show that this one will approach 1. Okay, we should divide everything by n, right?
N square
Just that.
n
We divide everything by n, we'll get
totally is n squared, but n for each term.
yeah. So we'll have, we do multiply this side by 1 over n, multiply this by 1 over n, right? So we're multiplying by 1. So we're going to have,
No, n 1 over n squared. So we can
oh yeah, put
give
1 in
n
each.
to the- yes.
Yeah, you're right. Smart idea. So then we'll get 1 plus 1 over n times 1 plus 1 over n over 1 plus 2 over n. Okay, this is all going to 0, right? So this is just 1. And here we have 32 times this one. We will multiply this by, I guess, 1 over n to the 5 over 1 over n to the 5, right? Something like this. Then we can put things together. So we have, I guess, 1 plus 1 over n over, wait, oh yeah, we have the 32. We already took that out. 2 over n. This 0, this whole thing goes to 0, goes to 1. So then we have just 32. So since 32 is greater than 1, we say by ratio tests or by absolute ratio test. They're all the same. By ratio test, divergence. Okay, cool. Determine whether each integral is convergent or divergent. If it converges, find the exact area that it represents. Let's make sure it's still working. Yeah. Sure. Okay. So intuitively, if you look at this, if it was just e to the x over e to the 2x, that would be e to the x over e to the x times e to the x. We'd have 1 over e to the x, which will obviously converge because it's approaching 0 very, very quickly, right? So, of course, we can even use comparison test for this, right? We have e to the x. Yeah, this is very simple by comparison test. Sorry, less. Yeah, less. Sorry. Okay.
Then we integrate this.
Oh yeah. We just integrate this. We should mention that
We can also write the integrate sign for each term because it doesn't matter.
sure,
They're all greater than 1.
right?
Yeah.
Dx, whatever. Okay, this one is so it's e to the minus x. Oh right. E is its own derivative, so we can just basically do minus e to the x, minus e to the minus x, right? Okay, really it's the limit as a approaches infinity of some a, but whatever. Let's use this notation. We can check our work by doing the derivative of this, which is equal to e to the minus x by chain rule will be equal to e to the minus x times minus 1. The minus 1s will cancel with this minus 1, and we'll get this, right?
So this converges.
This equals minus e to the minus x. Here, because we have a positive here plus a positive here, right? E to the 0, like if you look at e, it's always positive even, whatever. And we have making the denominator bigger makes the whole thing smaller, so we can make it bigger by just removing it. Anyway, so I don't know why I put x there. Should put infinity and subtract minus e to the...
So it's 1 here.
E to the minus infinity is equal to minus 1 over e to the infinity, which is just infinity, and this whole thing is just 0. And minuses cancel. We have e to the minus 0, that's just 0. And e to the 0 is 1, so it's equal to 1. Oh!
Still, we need to find the exact
Yeah.
value.
They want the exact... Sorry. That's my bad. Yeah, just use substitution, right?
Substitute for e to the power x. Or you can divide the 3 first from the numerator and denominator first, and then substitute the n equals e to the power x divided by square root of 3. I mean, you can pull the 3 out first, because we will use the, I guess, tangent inverse x substitution again.
What? Trig sub? No, you don't need trig sub for this. Come on. There's no way.
Okay, we can just simply try to substitute e to the power x first. Yeah, so this becomes n squared plus 3. Oh, it's u, not n, so x.
Right, because e to the power of 0 is 1.
Yeah, so it's from 1 to infinity. U over u squared plus 3. Du over u, because this term is u. Dx equals du over u.
Okay, now we have this one, which...
We will use the trigonometric substitution.
trigonometric...
Sure, yeah, we have to pull the 3 out.
You mean u substitution?
Trigonometry is substitution. We can divide the 3 out. So this becomes 1. This becomes u over square root of 3 and then square.
Sure. And then it's just arctangent, right?
And some factor.
We're dividing this by 3, so
Yep.
we
want to make this 1, so that's why we divide it by 3.
Yeah. So that means we can take this 1 over 3 out.
Yep.
So we have 1 over 3 times
U over...
let's do that later.
Okay.
Yeah, root 3, right? Okay, and now basically we use reverse chain rule. We should multiply by the antiderivative in terms of the input, and then we multiply instead of by f prime x by 1 over f prime x, so that when we think about the reverse derivative, when we'd multiply by f prime x, that would cancel.
So we should times root 3 outside.
Yes, we'd multiply by 1 over root 3, which is root 3, yes. So we'd start with arctan e over root 3. And we would multiply this by 1 over, like 1 over the derivative of this. The derivative of this is 1 over root 3, so you need 1 over root 3 is just root 3. And this is, of course, evaluated from, and that we can put, like, the third is outside the valuation, put it back inside the valuation. None of it matters, right? Evaluating it from 1 to infinity, right? So that means we have a third times arctan of well, infinity over root 3 is just infinity, right? 3. If you think about arctan, it looks like this. It looks like this one. So, I know. Arctan 0, 0. Yeah. Arctan 0, 0. So it looks like this. Yeah. So this is pi over 2. So the limit as, so this is, I'm writing infinity. What does this mean? The limit as a approaches infinity, which would be pi over 2. So we can just put pi over 2 here. And we should subtract arctan of 1 over root 3. That means tangent of something equals 1 over root 3.
Over 6.
So we can use our special triangle. Basically, we cut an equilateral triangle in
30
half.
degrees. Yeah, here's 1. Here's root 3. So this angle is 30 degrees. 30 degrees is pi over 6.
Yeah. Okay. So just to explain, this is 2, right? The triangle was cut in half, so this is 1, and by Pythagorean theorem, this is root 3, right? This was the 60-degree angle, or before it got cut, so it's pi over 3, and this is pi over 6 because it's half of the equilateral. Of course, this doesn't look like it was half of an equilateral triangle. I didn't draw that good, but anyway. So in this case, we see, of course, the tangent of pi over 6, as he mentioned, 30 degrees, is going to be 1 over root 3, which is why pi over 6 will be what will happen. So we're going to have a minus 1/3 of pi over 6 times
root 3.
yeah. So we're going to do this one minus this one. We can say we have a lot of similar terms. If we factor out a third and the pi,
And
we're
root
just
3.
and root 3.
Yeah.
Yes. Point. Then on the here, so you just have
1/2.
the 1 over 2. That's it. That's all that's left.
And minus 1/6. Yeah.
This is, of course, just, we can write this as 3 over 6, so it's just 2 over 6, which is a third. So it's just root 3 pi over 9. Right?
Yes.
Okay. That was just 6 marks. Here's an 8-mark question from Fairtown. More fun. Let's see how much is left. Wow.
Okay, so today we are here to over. Next video will be tomorrow. I will see you soon.
Okay. So we should just go over everything, I guess. You can continue, doing the work.
I will go my business.
I'll try and continue doing the work. Although he provided us a lot of guidance with the trig stuff, so thank him for that help. Yeah. Honestly, all these integral ones, you just need to practice them. I don't think it's... You can watch my integration videos from before. Yeah, I think I'll just skip this 8-mark one. Yeah, just to give some intuition on what you should do. We have here x to the 4 minus 1. That's the same thing as x squared minus 1 times x squared plus 1, right? And we have... Yeah, this is just some trig substitution. Not easy trig substitution, probably. Yeah. How would you even do this? X to the 4 minus 1. I see. So basically, what you can do is... we usually, when you have x squared minus 1, right, you know that you should sub in... what was it? I think it was tangent, right? Because if we let x equal tangent theta, then we have a square root of 10. Oh, sorry, secant. We let it be secant because we know that sec theta, because then we know sec squared theta minus 1 is equal to square root 10 squared theta, which is equal to 10 theta. And the reason why this identity is true is because if we're saying these two things are equal to each other, that means that sec squared minus 1 equals 10 squared. We're saying, I guess, sec squared minus 10 squared equals 1, I guess. And I guess this is 1 over cos squared minus sine squared over cos squared equals 1. If we multiply both sides by cos squared, then you'd have a 1 minus sine squared equals cos squared, or 1 equals sine squared plus cos squared, right? This is a famous one. So this is true. So yeah, so usually it's 7x equals, but in this case, we have x to the 4. So what you'd actually want to do is we want to let x squared be equal to sec theta, right? That would be the intuition. So I'll just show you guys my first step for what I would do. I would say that it's the integral of, yeah. Okay, I guess I'll just do this question, whatever. Let's just try it out, see how it goes. Integral from 1 to infinity of okay. So as I said, I'm going to let let x squared be equal to secant theta. Right. Therefore, we know that I guess x equals square root secant theta. So we have dx equals okay. The derivative of secant is complicated. Is it? No, sorry. It's not complicated. Derivative 1 over cos is equal to minus 1 over cos squared times minus sine. These cancel, so you just have 10 sec. Yeah. Derivative of sec is 10 sec. So you have 10 sec over 2 roots sec. But this is just going to be equal to 10 root sec over 2, right? So in terms of this x, yeah, we're just going to have to put in the root there. So it's going to be square root sec theta plus 1 over square root of sec squared. And we have 10, we have, let's move this over. We have 10 sec over 2 roots d theta. Okay. So from here, I guess we can make this just be tangent. That was the whole point. This is 10 squared. It's tangent. Oh, so that means this cancels here. That's beautiful. So now I have sec to the 1.5 plus sec over 2 root sec theta. We can. It would have been smarter to just. Wait, what? So this I should have just written as root 7. Oh, I wrote it here better. I'm stupid. I wrote the worst root. This can just be root secant. So then we just have root secant times root secant to secant, right? Plus root secant over 2. Why is there a 1 here? Oh, this is the integration models. Okay. So now we have the question of what to do here, which is not an easy question. Yeah. I think this is the right way to start the question. Can you
Post this video and then
discuss?
Yeah.
Oh, sure. Do you have an idea for what to do? Just
I have to look up the question again.
Let's say that you have this integral. Let's say this was the first starting position, right? What would you do? You have this integral.
I've never faced this situation before.
Okay. So I guess we'll try and look at like some online integral calculators or whatever to try and find the solution, and we'll come back to it. Before I check the solution, I want to quickly say that I didn't consider these integration limits. Yeah, so basically I should just write like this. Now I'll check the solution. I'll be right back. Okay, so it turns out that you need to know the derivative of hyperbolic tangent inverse. The inverse of hyperbolic tangents to solve this. So I'm just gonna skip this. Hopefully, we won't have anything that hard on the test. Yeah. Let's just hope. So we have an equals this. Prove by definition that it converges. So we have to show that for all epsilon greater than 0, there exists n greater than 0 such that any z whatever plus n greater than n. I mean, the fact that n's greater than n implies that it's plus, so I don't need this. Implies that an minus L is less than epsilon. Okay, so first of all, let's figure out what this diverges to. I mean, we have a linear function over a quartic function, so I'm going to take a wild guess that this will approach 0. So we're going to we're going to guess. This is a very, whatever. We're going to guess that L equals 0. So we need to show that we can make an less than epsilon. So let's start here. We can write what an is. It's 2 minus 2. This is our side, I guess. Squared plus n squared minus n. Okay. How do we do this? Okay. we can split it into 2 over this plus this. And we know that this is bigger or equal to this one, less than epsilon, right? By the triangle inequality. We can just delete the negative. It's not really important because, say by absolute, we can remove the negative. Okay. This term, I'm just gonna find an upper bound on this, or yeah, I'll find. Mm, Never mind. I don't know. This is so obvious. Okay, I can try and make this less than epsilon over 2, and this one less than epsilon over 2. Okay, so I have 2 over n squared plus n times n squared minus 3, and I want to make it less than epsilon over 2. Okay. Guess I'll multiply both sides by 2. And we should choose some n to ensure this. Okay. Okay, let's just expand this, and then we can use some stuff. Yeah. We can choose to make n, the minimum n to be this to be as big as we want, so keep that in mind. We can expand this to be n to the 4 minus 3n squared plus n cubed minus 3n. And let's put something bigger here. Something bigger is this. And the reason that I'm doing that is, let's say that, I mean, just the fact that n is greater than 0, right? And that these n's are positive integers, that means that this term is negative, this term is negative, this term is positive, this term is positive, right? So that's fine. And yeah, I mean, sure, whatever. I want to choose an n to make sure, yeah. Well, I know that for n bigger or equal to 1, which it is, since n is an integer, right? That's bigger than 0. I can guarantee that we can multiply both sides by n cubed. So I want to make the denominator smaller to make this bigger. So to make the denominator smaller, I can, these are both positive terms already. Oh, right, here I should have proven that this whole thing was positive. I mean, n to the 4 grows faster than everything else, so I can choose, I know that I'll be able to choose some n to make sure this is positive. In theory, like, you should find where that big N should be to limit it, but whatever, I mean, it's obvious, right? It's fine. There's gonna be some n where we can do this, and then we want to make the denominator smaller, so we should have n cubed plus n cubed in the here. So that's just going to be equal to 2 over n cubed, right? This is 2n cubed, which is less than epsilon, so we have 2 is less than epsilon, and I need to get to condition on n greater than n. Do this. N cubed is positive, and 2 over epsilon. So, okay. That is for this side. Now I should do this side, and then I should just make sure this is true and whatever condition I get from here is true. So, you can just do the same thing. There's just going to be an n on top, right? This is the same thing but with an n. So, n, 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 n. This just becomes squared. Okay. So we need also 2 over epsilon rooted to be less than n. We know that this number will be bigger than this number. So if n is bigger than this, that will imply that it's also bigger than this, right? So we can just choose. We need to choose n to be the maximum of this number, and whatever number that will make sure that this is positive. I mean, can we just do that right now? We want to make sure this is positive, right? Okay, one easy way to do this is to take the derivative of this denominator, right? Okay, and then take some ridiculously big n value, like n equals 100, right? Even 10, whatever, right? And then we have 10 cubed is 1,000, so we have 4,000 minus 60 plus 300 minus 3, right? So this is positive. So our function is going to be increasing, and wait. Oh, I want to see when is my function increasing. Well, yeah. I want to see when is this positive. I mean, we can clearly see that this term is what's going to matter, right? We can say that assume n is greater than, if n is greater or equal to 10, then I can say that okay, let's just do it. We want to see when our thing is increasing, so greater than 0, so we have 4n cubed minus 6n plus 3n squared. When is this greater than 3? So we can factor out an n here. You have 4n squared minus 6 plus 3n. Okay, and then I can plug in n equals 10. Or, sorry, I can say if n is greater than, if n is greater than or equal to 10, then I have, this will be positive, and this is going to have, is going to be bigger than or equal to 400, right? And this thing is going to be positive, so the whole thing is positive. Oh, okay. We can say that this has to be greater than 3, so this is going to be we have this thing is greater than or equal to 10 times 400 minus 6, right? And this is greater than 3 is clearly true. So therefore, we can just so at n equals 10, it's increasing. For the rest of its domain, it'll be increasing. And if you put in 10 into this function, you'll clearly see it's going to be positive. So if you have a positive function that continues to increase, then it's always going to be positive, which is how we can remove this things. So just to confirm, 10 to the 4. Okay, let's just write it. 1, 2, 3, 4, 10,000 minus 300 plus 1,000 minus 30. This is greater than 0, so we have a positive number that's continuing to increase. Yeah, I can just put a 10. And there you go. Sorry, choose big N. That's right. And you're done. And then you just have to go in the opposite direction. Start with this and show that that implies that, which implies dot dot dot, which implies this, which implies this, right? You want to go backwards to this, and you're done. Okay. Yeah. There might be cleaner ways to do it, but that's the idea. And in general, like, yeah, I mean, it's kind of like, I'm sure there's a theorem that if you have a polynomial over a polynomial, if the degree of the lower polynomial is higher than the degree of the top one, it will approach 0. That's like even yeah, but whatever. I don't think you're allowed to use that here. You should just do all this work. Okay, whatever. Okay. And Bn both converge. Bn is bounded. Wait, what? It doesn't say anything about whether An is bounded. I mean, oh, I see. We know Bn is bounded, but we don't know if An is bounded or not. But even if it's wait, what? An must be bounded. It's a sequence of numbers, right? A sequence of numbers that converges must be bounded. I'm confused why. Whatever, it doesn't matter. Okay. I'm gonna assume here that L equals AB. It's a very obvious assumption since this is just A and Bn, right? And N goes to A and Bn goes to B. So we're going to show that for all epsilon greater than 0, there exists n greater than 0, such that n greater than n and z implies that A and Bn minus AB. Oh yeah. They give us. I mean, we don't. This is that we don't have to suppose this. This is implied by the fact that but they're giving it to us so we don't have to cite the theorem. But this is implied, right? By the fact that any bounded converging sequence will. Sorry, any convergence. Okay. Any converging sequence will be bounded, right? That's just obvious. That's something else we can prove, but whatever. Okay, let's show this. So this one, an bn minus ab is less than epsilon. So we have maybe we can write it like this. Maybe what we should do is they gave us some information on bn. We should add and subtract bn. I should add and subtract a bn. Sorry. Yeah. Okay. Now let's group this with the minus and this with the plus. So now, okay, I don't know, I shouldn't have removed the absolute brackets. Forget this. Okay. I have an bn minus a bn plus a b minus a bn plus an epsilon. So now let's say it's factorial bn, an minus a plus here factorial a, b minus bn plus epsilon. And the idea of this proof is that's just that we know that bn is bounded, so we can say that we want to, okay, we can say that by the triangle thing, that this thing is less than or equal to this one, and this one is this thing. Let's also use properties of stuff to go here, and properties of absolute values. Okay, and so now we're here, right? We want to show that we can make this as small as we want. So bn, I see. So we can say, we can actually go further. Not even less than epsilon. This is less than c. CER is bigger than this. C is bigger than, not small, than bn for all of them. Okay, we know that there exists the c, so we can just sub it in here. Which is less than epsilon, right? So now it's just very easy. We can make this as small as we want, and we can make this as small as we want. Okay, let's say we want to make this whole thing less than epsilon over 2. So that means we should make this one epsilon over 2c. Could c be 0? Let me think. Maybe. Okay. Then there's this trick you should know in case stuff is 0, because you never know. We should say c times this is less than c plus 1, less than or equal to c plus 1 times this. Okay, less than epsilon over 2. So now we just have an minus a less than epsilon 2c plus 1. Okay, and then using the same steps for the other one, but instead of c we have absolute a, right? And then we're done, because we can choose here. Okay, you can write out the delta epsilon for an and for bn, which we're given. We're given that these things converge, so yeah, I mean, choose epsilon 1, because it's for all epsilon, right? We can choose epsilon 1 to equal this one, and choose epsilon 2 to equal this one, and once you've chosen both of your epsilons, we can there's going to be some corresponding n value that will guarantee that this is true. There's going to be n1, there's going to be some n2 that will guarantee that this is true. We can take the maximum of n1 and n2 to be Rn, and then we're going to get both of these will be implied, and then we just work backwards, and we get all the way back up to here. So yeah. I'm not going to rewrite it backwards, just everything I did, just do it in reverse, basically. Okay. Determine if the following series converge or diverge, fully justify our work. Okay. So this one is okay. This to me, we can use. It seems to me like we can just use div test to show that it diverges. We can show that the limit as n approaches infinity of the general term is equal to like 1 over 1 plus 3 over infinity is 0, 0 to the infinity. Like this is just clearly just. Oh, I guess. No, yeah, it would be indeterminate form if this was 1 to the power of infinity, but 0 to the infinity is just 0, right? So this fails the vanishing condition. Therefore, it fails. It just failed div test, I guess, or succeeds, depends on how you want to view it. Yeah, it will diverge. Okay. Next question. Okay. Okay. This one will not approach 0 either, as n approaches infinity. So I guess we can try and do div test again. Why was this 6 marks? It doesn't make sense. Whatever. Anyway, like this seems harder than this one, and this one's worth more marks, but I don't know. Whatever. Let's try and use div test again. Do the limit of the general term as n goes to infinity. It's gonna be basically like plus or minus minus a half, which is just plus minus half. So the series is gonna alternate between half minus half, half minus half, which is not 0, right? So like this limit doesn't even exist, basically, right? So yeah, this clearly diverges. This isn't that rigorous, I guess, but if you wanted to show that this limit doesn't exist, I don't know. I guess you could split it up into the limit as n approaches infinity of minus 1 to the n times the limit as n approaches infinity of 2 plus n over 1 minus 2n. This you can easily show is 1 minus 1 over 2. And this one is always going to be plus or minus 1, so you could just say this diverges. And then you can just say that divergence times convergence, where the convergent does not equal 0, that's important, will always equal divergent. Oh, this leads us back to that multiple choice question, where they didn't specify that this is not equal to 0, right? So yeah, whatever, diverges. Diverges by div test. Okay, this thing. Okay. this seems to just be 2n minus 1 factorial over 3n minus 1 factorial. Unless I'm wrong. We put in 1, we got 1 factorial, 2 factorial, yeah. If you put in 2, you get, wait, no, sorry. If you put in 2, it's 6, so I'm wrong. What am I even doing? Sorry. I see. Okay. Okay. So I guess the important thing to notice here is that this looks similar to 2n over 3n, right? Which is very similar to 2 over 3, right? So this appears to be similar. It will behave at infinity like a geometric series. So I would use ratio test to show that the limit of the ratio will approach 2/3, which implies that it will converge, right? They don't care what it converges to, just if it converges or diverges. So let's try and do that. We'll do the absolute ratio test. I have 1 times 3 times 2n minus 1 times 2n plus 1 over 2, 5, 3n minus 1, 3n plus 2, plus 1, sorry. Because this is just increasing by 3 each time, right? This is increasing by 2 each time. Divide that by our normal term. And we have limit as n goes to infinity. Absolutes. I don't know why I put a 2 there. That's my bad. This is plus 2. Okay. So this cancels here, right? And this cancels here. Wait. Oh yeah. So now I just have the limits n goes to infinity of 2n plus 1 over 3n plus 2. This is just 2/3. I don't know. If you want to do it rigorously, I guess just say it's 2 plus 1 over n over 3 plus 2 over n. These go to 0, so you have 2/3, whatever. Okay, so this is less than 1, whatever. Therefore, converges by ratio test. Easy. Okay. How many questions are left? 1, 2, 3, and a bonus question. Just 4 questions? Easy. Okay. We'll finish soon. How much battery is left? Okay. We have 46 minutes left to finish everything. Okay. I'll lower the brightness a bit. Get some more time. I'll put battery saver on. Okay. Sure. Okay, let's try and go fast. Find the radius of convergence and the interval of convergence for the following power series. Okay. So, in order to solve this question, let's first find the radius of convergence. First of all, we can say that our general term is 1 over n root log n. and we can say that our center is equal to 1. Now the next thing we should do is try and figure out when or when not this will converge or diverge, for which x values. Let's think. Yeah, we can probably just use ratio tests. In general, for these, you just use ratio tests. So let's do it. Okay, so now that we set up the ratio test, we can cancel some stuff out. We have now x minus 1 times n root ln n over n plus 1 times root ln n plus 1. We want to see the limit as n approaches infinity. Okay, because n's approaching infinity, I'm gonna be a bit... Okay, I guess I shouldn't do that. Let's divide by n, so this becomes 1, that cancels, and this becomes 1 over n, which goes to 0, and then cancels with this, right? Or it becomes just 1, right? So the 1 is relevant to the thing. If you have 1 times something, it's just itself. Okay. So now we have this one, x minus 1 times root ln n, or root ln, never mind, ln n plus 1. We can write this as x minus 1 times square roots of ln n over ln n plus 1. Okay. So we can write that as times the square root of we can, there's the logarithm rule that, oh, never mind, that's if it's, should be, yeah, never mind. We can say that the square root function is continuous, so we can put the limit inside. And when we put the limit inside, we can put the limit inside the logarithms, which are also continuous. Or, never mind. I want to know what the limit as n approaches infinity of ln n over ln n plus 1. So in order to find this out, I should Okay, I'm gonna pause the video and resume when I figure it out. Okay, so we can just use L'Hopital's rule here. Uh, so we should say we're doing L'Hopital's rule, infinity over infinity. It's this version. This is our version of indeterminate form, because ln approaches infinity. So then we just put the derivatives. So this is just n plus 1 over n, which is 1 over, sorry, yeah, 1 plus 1 over n over 1. This goes to 0, so it's 1. So then this is 1, so this is 1. So we just have x minus 1. We need, this is our ratio, right? So we need the absolute of x minus 1 to be less than 1. At 1, the ratio test doesn't tell us anything. When the limit of the ratio is equal to 1, it doesn't tell us anything. So we have to do that minus to figure out if we have this or this or this or this interval of convergence, right? For now, we just want to figure out what's inside. So we have minus 1 less than x minus 1, just less than 1. So add 1 to everything. Okay. So this is our base. Now we should just check for 0 and 2 what happens. Obviously, wait. Okay. Um, hmm. Yeah. We need to see at 0 and 2 what happens. Okay, the radius of convergence is 1. We just found that because we have 0 to 2 and our thing is at 1. R equals 1. That we just found. Now we just need to find the interval of convergence. So if we put in 0, then you have minus 1 to the n times 1 over n root ln n, which will converge by alternating series test. Our thing is strictly decreasing, and it approaches 0. So yeah, this is for 0, so 0 is valid. Yeah. So we can have x equals 0, that's fine. I'm curious why you can't have, like, let's say minus 0.5. I see. Then the exponential term will blow up. That makes sense. We need to make sure that the magnitude of the inside is less than 1, or else it'll grow so fast that this term will be irrelevant, right? That's cool. So then we should see what happens if we plug in 2. Then we have just 1 over n root, because 1 to the n is just 1 ln n. We need to see what happens here, if this will converge or diverge. This term grows like very slowly. 1 over n will, yeah, this diverges, right? Because this is gonna be greater than 0, so we can say, like, yeah, at some point ln is more than 1. Yeah, because n is greater than 0. That means ln is increasing, and ln of 3 is greater than, like, if you look at ln, like, ln of 1 is 0. Oh, I see. I need to figure out where it's greater than 1. I need ln n to be greater than 1. That means I need Um, let's see, when is ln n equal to 1? That happens when n equals e, right? So we need n to be bigger than e, so yeah. The first term is irrelevant, and then the next term will be n equals 4, and at that point, starting there, we can just use comparison test. This is going to be more than 1 over n, and this one is just a p series which diverges. It's the harmonic series, and it diverges because the power of n is less than or equal to 1. So it will diverge. Yeah. So this is an interesting case where we have one of these two options. So we had that 0 is fine, but 2 is not fine. Sorry. 0 is fine, but 2 is not fine. So this is our interval of convergence. I equals this, and R was 1. This is your final answer. Okay, we have 41 minutes left until my battery dies. 3 questions. Okay. Show if n is greater than 0 and n is convergent, then ln of 1 plus n is convergent. Okay. Then this is just comparison test, an greater than ln 1 plus an. We can raise both to the power of e. And, I mean, yeah. I don't know why I did this. 1 plus n. So we need to see when is e to the an minus an greater than 1. I mean, this is obvious. That is, it'll be true for some n greater than 0. Yeah. Okay, let's solve the thing. Let's say we had e to the x minus x is greater than 1. Then I have oh, we're given that an converges, right? Okay. I need to show that this is true. So an converges. So but basically, the intuition is that if you plug in any positive number, so you have like e to the power of a positive number greater than 1 plus the positive number. That's not necessarily true, is it? I don't know. Maybe this is not how you do it. Sorry. I'm gonna pause the video and be right back. Okay, so I think I figured out what we have to do. So an approaches 0 because it's convergent. Convergence implies that the general term approaches 0. So therefore, we should show that if an approaches 0, then ln of 1 plus an convergent. Okay, I'll think some more and continue the recording. Okay, so I just found the answer online. You have to go fast. I have low battery. Let's lower the brightness a bit. If you do ln of 1 plus an over n, we have the limit as n approaches infinity is equal to the limit as x approaches 0 of ln of 1 plus x over x. This is because as I said before, by the vanishing condition, when n approaches infinity, we have we have that an approaches 0, right? So here we can just use L'Hopital's rule, which is 1 over 1 plus x over 1, and still have limit as x approaches 0, and then because we can just plug it in because it's continuous. Okay, done. So therefore, if we have something over convergent equals convergent, then we have something equals convergent times convergent, which we know we even proved it in this very test that this is actually convergent, right? So therefore, this converges. Okay. And my laptop is really running out of battery. I don't know if we have time for these questions. Prove that the sequence diverges. Come on, this is a stupid question. I mean, yeah, we can even say that this is, I don't know, n squared plus 1 over n plus 4 is greater than plus 1. Let's say, I don't know, this, since we can say n is greater or equal to 1. Okay, so then this is equal to n plus 1 over n plus, oh my god, I'm so stupid. I guess the point, I don't know what the point was at. Here I can make a 4n squared. Here I can make it n squared, right? So then we have, wait, sorry. Here I can just make it smaller by removing the 1 altogether, right? Sorry, what am I doing? This. And now we have, this is just n over 5, and the limit as n approaches infinity of n over 5 equals infinity. I mean, like, this is obvious. Like, take arbitrary number a. We can make n to be 5a plus 1, and then 5a plus 1 over 5 is bigger than a, right? So for any arbitrary a, our thing is bigger than it, so obviously, like, that's the basic delta epsilon. And okay, we have a little bit more battery left. Hopefully we can do this last question. It's convergent. Okay. Okay. So this is just let's do ratio test. Okay, we can ln n plus 1 minus ln n plus 1. This is bilog properties, right? And we need this to be, we need b to the ln n plus 1 over n, limit n goes to infinity, we need this thing to be, for convergence, needs to be less than 1, and then we should check at the edges. So, okay, we need, okay, the b to the power, let's just consider positive b for now. Yeah, they want all positive values of b, so b is positive, and a positive thing, positive number raised to any power is still positive, so I can just remove these absolute values that are not necessary. Okay, the limit of this one, we did this exact same one, I believe. Yeah, limit as n approaches infinity. Okay, I mean, we showed that. Oh, never mind. This, yeah, then you could. This is continuous. Put it inside. This goes to 1, so this goes to 0. So we need b to the 0 to be less than 1. But of course, that is true for all b. So of course, b has to just be an element of the of z plus, right? Z plus is our solution set. Yeah, because sorry. R plus, not Z plus. Any real number. Because any real positive number to the power of 0 will be equal to 1. Oh, equal to 1. Sorry. Do we need it to be less than 1? Okay. So... Huh. Sorry. Yeah, we need it to be less than 1. So the question is b to the 0 okay or not? Uh, b to the 0 is 1. Oh, this is just... Yeah, this will never converge, right? The solution set is the empty set, I think. Unless I'm wrong, because any constant value to the power of ln n, right? N is going to infinity. Wait, what? Hmm. Um, yeah, I think this just never works. Because the reason why this never works is if you have any positive number, right, to the power of uh, like ln n is approaching infinity, right? Like we can even look at the general term, right? Let's use div test, right? Our general term is b to the ln n, right? And the limit as n approaches infinity is equal to b to the power of infinity. Oh, I see. Yeah. If b just has to be, I think, like this. This is the solution. Because if b is 1, if b is 1, then you just have 1 plus 1 plus 1 plus 1, which will diverge. If b is more than 1, the general term will not approach 0. And if b is less than 1, you're fine, because it's going to approach 0, will approach 0 fast enough, probably. If you do... one second. Okay. Okay, the way I would do this is I would do comparison test to prove that this range is okay. I would say that I would choose some n to start with, right? Let's say let's say mm, let's say we have some number here that's between 1 and 0 and 1, right? Let's try as 1 over n, where n is greater than 1. And we can say that this is to the power of ln n. We can write that as 1 over... Oh, these are different ends. We can say that ln n is going to be... Okay, my laptop is about to die. I'm pretty sure it's 0 to 1. I'll try and Google the solution quickly. I'll be right back. Quick note that b is equal 0 is no good because you have 0 to the power of... wait, actually... 0 to the 1 equals 0 to the 2. That will converge, actually. Should it be 0 here? Now I'll try and Google